Good afternoon to all. Am I audible? Am I audible? Then let us start the class. So today I will discuss the one of the network theorems, that is maximum power transfer theorem. So in order to know what is maximum power transfer theorem, in order to understand this maximum power transfer theorem, we must have the knowledge of Thevenin's theorem. So if we know how to verify Thevenin's theorem, then only we can understand this maximum power transfer theorem. Okay, so first of all, let us see the statement of maximum power transfer theorem. So it states that the maximum power is delivered from the source to the load when the load resistance is equal to the source resistance. So in order to understand the statements, let us see this circuit. You can see this circuit. Just a second. Okay, now you can see this circuit. You can see there is a voltage source. There is a voltage source here. Let us assume this is our positive terminal and this is our negative terminal of this source. So there is a voltage source here. Okay, so this is our source. My cursor. So better I will write here so that it will be more easy. So this is our source. I'm unable to write source here. Okay, I will not write. I will erase this. Okay, this is our source, voltage source. This is our source. This is our source. And this is our resistive load, RL. RL is the resistive load. So there is a source, there is a load. Okay, so to make it, I will at least write, I will write S here. S means source. I will write L here. L means load. Okay, this is L. L means load. S means source, let us assume. So this is our source, this is our load, and here you can see RS. RS is the internal resistance of the source. Okay, RS is what? It is the internal resistance of the source. Okay, now when source is connected to the load, here when the source is connected to the load with some internal resistance RS, okay, maximum power will be delivered to the load. So the power has to be delivered from where? It has to be delivered from source to load. Okay, power has to be delivered from source to load. Okay, so whatever power that is delivered to the load, that power will be maximum. Okay, that power delivered by the source to the load will be maximum. Power delivered by the source to the load, it will be maximum whenever load resistance, what is load resistance here? RL. Whenever this load resistance RL is equal to the internal resistance of the source. What is the internal resistance of this source? That is RS. So whenever, okay, whenever, if this is my RL, if whenever RL is equal to RS, then power delivered to the load will be maximum. Okay, PL will be maximum, I can say. I wanted to write P here, but I couldn't write. It's okay. Okay, power delivered to the load, PL. It will be what? PL will be, let us assume PL is the power in the load. Okay, that will be maximum. Okay, I succeeded to write max. Okay, so once again let us see the statement. What is the statement? It states that maximum power is delivered from what? From source to load when load resistance is equal to what? Source resistance. Okay, so whenever RL is equal to RS, okay, if RL is the load resistance, RS is the internal resistance of the source, whenever RL is equal to RS, what will happen? The power delivered to the load will be maximum. I hope you are able to understand what I am speaking. Now, what is the current? Current in this circuit, let us assume some loop current I. Okay, so let us assume some loop current I have assumed in clockwise direction. And as I have already told you, let us assume this is our positive terminal and this is our negative terminal. Okay, so what is the current now? Total I is the only current in this closed loop. There is only one loop. So I is equal to what? Total voltage V. Okay, total voltage V divided by total resistance. RS and RL both are connected in series. Therefore, V divided by RS plus RL. V divided by RS plus RL. So what is the current in this circuit? I is equal to V divided by RS plus RL is the current. Now what is the statement? What did I say? I told you that maximum power will be delivered, according to the statement, maximum power will be delivered to the load from the source when load resistance is equal to the source resistance. So first of all, let us calculate the power delivered to the load. Later on, we will calculate the maximum power. Okay, so what is the power delivered to the load formula? That is there in the other slide. So what is the power delivered to the load? Power delivered to the load. What is your load here? RL, resistive load. RL means resistive load. So power formula is I square R. Okay, P is equal to I square R. So I square into what is our R? R is our RL. Okay, so power in the load is P is equal to power delivered to the load from the source is I square RL. So this power delivered to the load, we can't say it is maximum, but in general we already know power formula is I square R. So that's what I have written here. So power delivered to the load is I square RL. So what is I? Just now we have seen in the previous slide, what is I? I is what? I is equal to V by RS plus RL. So substitute that in the next slide, next equation, power equation. So what is I? V square by RS plus RL square. Okay, because here it is I square is there. So V by RS plus RL whole square I might have written. I didn't write like that, but you can even write like that. So V by RS plus RL whole square into RL. You can write like that. So this is the power delivered to the load. But according to the statement, what is mentioned in the statement? Power delivered to the load from the source, it will be maximum when load resistance is equal to the source resistance. So that has to be, that we have to verify now. So we already, I don't know whether you might be knowing or not, maximum power, if you want to determine the maximum power, okay, then what you have to do is you must differentiate maximum power with respect to the respective variable and equate it to 0. So what is our variable here? What is our variable here? Load is our variable. Okay, what is our variable? Load. What is our load? RL load, isn't it? RL is our variable here. Okay, so we are talking only about the load, isn't it? So therefore divide this P. Okay, I'm sorry, not divide. Differentiate this P with respect to RL and equate it to 0 to determine the maximum power. Okay, To determine what? To determine the maximum power, differentiate P with respect to RL and equate it to 0. So what is P? This is our P. So d by dRL into P. What is P? V square into RL divided by RS plus RL whole square. Okay. Now differentiate it with respect to RL. If you differentiate it, you will get V square into RS plus RL square minus 2RL into RS plus RL whole divided by RS plus RL whole to the power of 4. So I hope you people who are attending this online class, you might be knowing how to differentiate. Okay, so you must have basic mathematical knowledge of differentiation. Okay, so if you do this, you can see this denominator term, you can send it to the right side, it will become 0. So what is left over is numerator term. So if you are writing, you can write it down, or I will proceed further. So what is left over is numerator term. If you are writing, you can write it down. So now further simplification, what is left over? So there in this above equation, you can even see what is it? Where is my cursor? Yeah, you can even send this v square to the right side because it is the you have taken it is multiplied with the rest of the terms. If you send it to the right side, that will also become 0. So what is left over now? So RS plus RL whole square minus 2RL into RS plus RL equal to 0. So you just expand the above equation. If you expand it, you will get RS square plus RL square plus 2RS RL minus 2RL RS minus 2RL square equal to 0. Just simplify it, you will get RL equal to RS. Okay, it's just a mathematical simplification, nothing technical, nothing related to electrical terms. Okay, this is simply mathematical simplification. Okay. So if you are able to differentiate and if you are able to simplify the above equation, you will get RL equal to RS. So to determine maximum power, what we have to do? You have to differentiate the max power, not maximum. Okay, you have to differentiate power with respect to the variable and equate it to 0. So our variable is the load resistance. So differentiate power with respect to RL and equate it to 0. And you just simplify it, you will get RL equal to RS. So maximum power is obtained at what condition now? We have verified it here. Okay, so maximum power is obtained at what condition? When RL is equal to RS. That is when load resistance is equal to the source resistance. Okay, source internal resistance, you can call it as simply source resistance. So power delivered will be maximum according to this derivation that just now what we have done. Power delivered will be maximum whenever load resistance is equal to the source resistance. Okay, so did you understand? Do you want me to repeat? If you want me to repeat, if you are unable to understand, you can mention in the chat box. Okay, now let us this is the verification of this is to whatever till now we have done, that shows us that maximum power will be delivered to the load whenever RL is equal to RS. Now let us see how to solve the numerical problem. What are all the steps that are to be followed to solve the numerical problem? Okay, so the steps that are to be followed for maximum power transfer theorem. First of all, whatever circuit that is given, you must consider that circuit. So let us assume this is the circuit that has been given. Okay, this is the circuit. Okay, so in this circuit, what is there? There is a voltage source, some resistance R1, some R2, R3 and RL. RL is our load resistance. RL is our load resistance. Now, first step what we have to do is for solving the in order to verify maximum power transfer theorem for the given circuit. Theoretically, for the given numerical problem, if a numerical problem is given, so if you want to verify the maximum power transfer theorem for that numerical problem, first step what you have to do is you have to remove the load resistance. Okay, that's what we used to do for Thevenin's theorem also, isn't it? So that's what is done for Thevenin's theorem also. So you have to remove the load resistance. So you can see in the first image RL is there, in the second image RL is not there. I have removed it. So first step that we have to do is remove the load resistance. That is step 1. Okay, step 1 is to remove the load resistance. After that, after removing the load resistance, what we have to do is step 2, find the open circuit voltage. That is, after removing load resistance, what we used to do, we used to determine the, in Thevenin's theorem, what we will do, we will determine the open circuit voltage, that is Thevenin's voltage. That's what here also we have to do. We have to determine the, across the open circuit terminals, we have to determine the Thevenin's voltage, okay, or open circuit voltage. So what is step 2? To find the open circuit voltage, that is Thevenin's voltage across terminals A and B. Okay, across terminals A and B. Okay, so after determining Thevenin's voltage, what we will do is step 3. We will go for step 3. In the step 3, what we are going to do is, say here what is there? There is a voltage source. So if voltage source is there, you must short circuit the voltage source for step 3. Okay, in step 3 what we have to do is we have to short circuit the voltage source, or if current source is there, we have to open circuit the current source. So either you have to short circuit or you have to open circuit the source, depending on type of the source. So if the source is voltage source, you have to short circuit the voltage source. If the source is current source, then you have to open circuit the current source. Okay, so since we have voltage source here, we have short circuited the voltage source. Okay, so you can see this R1, only R1 is left over, isn't it? So instead of drawing it here, you can draw R1 here also. You can draw R1 here. Okay, so I couldn't draw R1 properly. So you can even draw R1 here. Okay, you can draw R1 here. So in this branch, in between this terminal and this terminal, if voltage source is short circuited, what is left over? What is left over? R1 is left over. So you can draw anywhere. You can draw R1 here, or you can even draw R1 here, or you can draw R1 here. Okay, you can draw anywhere in between those two terminals. Okay, in between this terminal and this terminal, you can draw R1 anywhere. Okay, so simply if voltage source is short circuited, what is left over between this terminal and this terminal? In this branch only R1 is left over. Okay, so it's not doubt should not come to your mind. Some other thought may come to your mind. You may think that this R1 was earlier in here at this position, now its position has been changed. Such thoughts should not come to your mind. Okay, so because you can, in between those two terminals, wherever you locate the R1, it doesn't matter. Okay, so even if earlier it was here, you can keep it here itself. It's not okay. So even if you keep R1 here itself or change its position to here, both are same. That's what I'm trying to tell you. Both positions are same. Okay, simply anywhere in between those two terminals. Okay, these two terminals, this terminal and this terminal, here in this branch you can draw anywhere R1. Okay, so it's not compulsory that earlier where in whichever location R1 was there, you must keep R1 there itself. Okay, so no need to confuse from this image and from this in between. No need to confuse between these two images. Okay, so that's it. Now we have to short circuit the voltage source. After short circuiting the voltage source across AB terminals, we have to determine what? R Thevenin. We have to determine R Thevenin. So that's what in Thevenin's theorem, that's what we do. So RThevenin, open circuiting the terminals in step 2, determine open circuit voltage, and short circuiting the source, voltage source, and open circuiting the current source, determine RThevenin in step 3. Okay, so this is step 2 and step 3. After that, let us go for step 4. Okay, in step 4, now we have determined VThevenin, okay, open circuit voltage. We have determined RThevenin. So after determining VThevenin and RThevenin, we must draw what? Thevenin's equivalent circuit. What is Thevenin's equivalent circuit? Thevenin's equivalent circuit will be consisting of Thevenin's voltage source, okay, Thevenin's voltage source, and Thevenin's resistance. Both are connected in, how they are connected? Both are connected in series. So this is our Thevenin's equivalent circuit. Across its terminals we must connect what? Load resistance. That's what, this is our Thevenin's equivalent circuit. Thevenin's voltage and Thevenin's resistor are connected in series, and across those two load resistance is connected. That is Thevenin's equivalent circuit. So we must draw the Thevenin's equivalent circuit. Okay. Now in this circuit, in this, it's a closed single loop, isn't it? It's a closed single loop circuit. So current, your wish, you can assume any notation. I have assumed IL. Okay, IL is my notation. Why I have assumed IL? The reason behind that is, here our aim is to prove that maximum power will be delivered to the load when load resistance is equal to the source resistance. Already we have proved it from the earlier derivation that we just now, which I have explained it to you. So in that derivation we have already proved that load resistance is equal to source resistance when maximum power is delivered. Okay, so that's why instead of simply writing L, I have assumed here IL now. Okay, now what's our maximum power theorem? According to maximum power theorem, maximum power will be delivered when RL is equal to RS. What is RS now in this in this circuit, in this above circuit? What is RS? RS is RTH. Okay. So in step 4, simply we have to draw the Thevenin's equivalent circuit. Nothing else we have to, there is nothing else is left over to do there. Okay. So simply draw the Thevenin's equivalent circuit in step 4. In step 5, you just mention RL is equal to RTH. So instead of RL, what can I write now here? I can write RTH. Instead of RL, you write RTH. Okay, RTH value in step 5. Okay. So now let us go to step 6. So in step 6, we will determine the maximum power. So what is load current according to the above circuit? Veronica. Okay, so I have copied this circuit from previous slide. So in order to show you how to write the load current equation, see, um, see here IL, let us assume load current notation as I have already told you, that is IL. So what is IL? IL is equal to what? It is the only current in this closed path, isn't it? In this closed path, it is the only current. So total current is IL here. Okay, so IL is equal to total voltage. What is total voltage? VTH. So VTH by RTH plus RL. Okay, so VTH by RTH plus RL is the V by R. That's it. Nothing else. Okay. I is equal to what? I is equal to V by R. I is equal to I is equal to V by R formula we already know. So So what is V? What is V? V is VTH. What is our total resistance? What is total resistance? RTH and RL. Both are connected in series, isn't it? So VTH by RTH plus RL. Okay, VTH by RTH plus RL. That's what I have written here. So now we already know maximum power will be delivered to the load when RL is equal to RTH. So instead of RL, I will erase all links. Instead of RL, now what you can write? You can write RTH. Okay, instead of RL, write RTH. So VTH by RTH plus RTH, what is it? VTH by 2RTH. VTH by 2RTH. So you can write VTH by 2RTH, or if you want, you can write even RL. Actually, you should not write RL. Why? Because we don't know the RL value here. We have not even determined the RL value. So if you know the internal source resistance, means if you know the internal source resistance value means R Thevenin. If you know the R Thevenin, so R Thevenin is nothing but RL. Okay, if R Thevenin is nothing but RL. So RL will be equal to RTH. RTH cannot be equal to RL. Means if you know the RL value, if RL is 3 ohms and RTH is 2 ohms, okay, even though RL is 3 ohms, you forget about 3 ohms, okay, you can't keep the load resistance fixed value, okay. So you must always, for not to verify maximum power transfer theorem, the load should be variable load. Okay, you must always take variable load. It should not be fixed value. As just now I told you RL is 3 ohms. So you can't consider that. Okay, 3 ohms. Okay, so it should be always variable. You can't give fixed load resistance to verify maximum power transfer theorem. So if load resistance is fixed, it cannot be equal to, it will never be equal to RTH. So for RL to be equal to RTH, RL has to be variable. Okay, it has to be variable. It should vary. Okay, so if you are if you write like this, okay, if you write like this and instead of RL, if you substitute the value of RTH, whatever RTH is there, 2 ohms, 3 ohms, 4 ohms, whatever, that if you are able to substitute, and after that, even though you are writing RL value, but you must substitute the RTH value. Okay, you must substitute the RTH value. Okay, so I hope I am not confusing you. So if anyone is unable to understand, you just mention in the chat box so that I will repeat. So now maximum power formula. What is maximum power transfer function according to maximum power transfer theorem? Okay, according to maximum power transfer theorem. Okay, so maximum power will be delivered to the load when RTH is equal to RL. Just now we have seen IL equation. What is IL is equal to VTH by 2 RTH. Okay, so what is power formula? IL square into RL. Instead of IL, what you can write? You can write VTH by 2 RTH whole square. So VTH square by 4 RTH square into RTH. So here RTH square is there in the denominator. In the numerator, RTH is there. Okay, RTH square is in the denominator and in the numerator RTH is there. You can cancel. So what do you get? P max formula is VTH square by 4 RTH. Okay, maximum power formula. Okay, so to verify maximum power transfer theorem, maximum power formula is what? P max is equal to, okay, P max is equal to VTH square by 4 RTH, and load current formula is this. No need to write the next equation. Actually, if you write this next equation, this is IL. If you write the next equation, you may get confused. Okay, you may get the next equation means VTH by 2 RL. If you write VTH by 2 RL, you people may get confused. It's better if you write IL formula as VTH by 2RTH. IL formula is VTH by 2RTH, and maximum power formula is VTH square by 4RTH. I'll remove this circuit. So this is it. Now let us solve the numerical problems. So this is the given numerical problem. Find the value of RL for the maximum power transfer and calculate the maximum power. Okay, you have to determine RL value and you have to determine maximum power transfer to the RL. So here you have to apply maximum power transfer theorem to simplify this circuit. Okay. Okay, this is the given circuit. You can see a voltage source of 3 volts, a resistor of 2 ohms, another resistor of 2 ohms, 6 volts voltage source, 2 ohms resistor, 10 volts voltage source. RL value, if you see here, they didn't give the RL value. They have asked us to determine the RL value. And if you have heard the class just now, which I have already, what I have discussed in this class, if you have heard me, then you might have understood that RL is nothing but RTH. RL is nothing but what? R Thevenin. Okay. So let us proceed. Now I will take that circuit and I will copy it in the next slide. Okay, so it is already there. Okay, so now, so first of all, what we have to do, we have to follow the same procedure which we followed for Thevenin's theorem. In step 1, we have to calculate Thevenin's voltage. So what we have to do, first of all, we must open circuit the load terminals. We must open circuit the load terminals. Okay. And what we have to write across the load RL? RL is removed. What is left over? AB terminals are left over, terminal A and terminal B. So across terminal A and B, what is there? What is there? It is open. So you just write VOC or VTH. Across terminal A and B, you write VTH, okay, or VOC. So now we have to determine VTH or VOC across terminal A and B. We have terminal A and B are not mentioned in the question. Okay, simply we have removed the load. After removing the load, what will happen? It is open. This portion is open when load is removed. This portion is open. So you just give some notation A here and notation B here, and you assign your own signs. I have written plus here and I have written minus here. It's our wish. Okay. It is our wish. We need not worry about signs. I have assumed terminal A as positive, terminal B as negative. Okay, open circuit. I have open circuited the terminal. I have removed the load. That's why I have got these terminals A and B. Open circuited terminals, I can call them as. So I will just copy this. I have to determine what now? VTH. So let us see how to determine VTH. Now, so how to determine VTH? So if you observe here, these two terminals are open. So in open terminals, and we already know no current will flow through the elements which are in the open terminals. If you see from positive terminal, if you move like this and if you move like this in anti-clockwise direction, I'm moving in anti-clockwise direction. Okay, I'm moving in anti-clockwise direction. From positive terminal, I will erase and I will draw in such a way you will be able to understand. From terminal A, I have started my journey. At terminal B, I have ended. So how I am traveling? I am traveling in anti-clockwise direction. Okay. And since terminal A and B are open, therefore, if you see in between terminal A and B, there is a voltage source of 10 volts. Okay. And there is a resistor of 2 ohms. In this resistance of 2 ohms, no current will flow. Why no current will flow? Why? Because it is connected to open terminal. Okay, resistance is connected to open terminal, so no current will flow. But if you observe this 2 ohms and 6 ohms, they are connected to a closed. You can see a closed path here. Okay, you can see closed path. You can see closed path. I'm sorry, this is my cursor. I don't know why, but it won't listen to me. So you can see closed path here. Okay, so this 2 ohms and of course forget about the voltage source, but in this 2 ohms definitely current will flow. Okay, now let us apply KVL in this closed path. Let us assume current I in this closed path. Okay, loop current, I have assumed loop current here, loop current I. So applying KVL in this mesh. Okay, this is a mesh, isn't it? This is my mesh. This is my mesh. So in this mesh, I have assumed current I. So let us assume current is in clockwise direction. You can see here, this is positive, this is negative, and this is positive, and this is negative. So what I can write? 3. Okay. So actually I should write -3, or I can write, okay, -3 plus positive and negative, isn't it? So 2 into 2 is R. R into I value is how much? I don't know. So I, okay, 2 into I plus another 2 is there, this resistance. 2 into again I, okay, again I, so see here, this was negative to positive, current direction was upward. Okay, current direction was upward. I will clearly draw it so that whoever is listening to this class, they will be able to understand. So I will just join this here. So you just observe the current direction is upward. Okay, this is downward. So current is traveling from negative to positive. Okay, from negative to positive for this source. If you observe here, current is traveling from positive to negative. Both are opposite, isn't it? Both are opposite. Therefore, okay, therefore, here you must write +6. Okay. So two sources are there in that loop. How many sources are there in that loop? How many sources are there? 3 volts voltage source and 6 volts voltage source is there in this loop. Two sources are there. Okay, 3 volts and 6 volts voltage source, and 2 resistors are there. What are those 2 resistors? 2 ohms and 2 ohms. Total how many elements? 3 volts, 2 ohms, 2 ohms and 6 ohms. Total 4 elements. So you must get 4 voltage terms here. So that is minus 3 plus 2 into I plus 2 into I plus 6 is equal to 0. That's my equation. You take minus common, you will get 3 minus 2i minus 2i minus 6 equal to 0. That's what I have written here. You see, 3 minus 2i minus 2i minus 6 is equal to 0. Simply, if you know how to write KVL equation, that's it. No need to follow me. So everyone will not think in the same pattern. Okay, so the way we think differs from person to person. So this is it. So whatever equation that I have written, for that explanation I gave it to you. Okay, so 3 minus 2i minus 2i minus 6 is equal to 0. So you just simplify it, you will get I is equal to minus 0.75 amperes. Okay, I is equal to how much? So here you can see minus 2i means minus 4i. Okay, minus 4i. Minus 6, you can send it to the right side, it will become 6. And if you send 3 to the right side, it will become minus 3. So 6 minus 3, you will get 3. 3 divided by 4. Okay, 3 divided by 4. So it is minus 4 actually. 3 divided by minus 4. Okay, so you just solve it. 3 divided by minus 4, you just do it. So you will get 0.75. You can solve it and you can mention the answers in the chat box, whoever is listening to the class. So I value, how much did you get? Minus 0.75 amperes. And now to find VThevenin, actually our aim is to determine VTH, that is VThevenin, across what? AB terminals. Now once again I will copy the circuit here. So I have copied the circuit. You just observe here. What did I assume? I have assumed A terminal as positive, B terminal as negative. So according to me, whatever I have assumed, according to me, the current should travel. Okay, current should travel. So the current will never flow. Actually, current will never flow in the open terminals. Okay, so even if you connect any whatever elements that you connect, even if there is a voltage source across the open terminals, current will never flow. Voltage may be there, but current cannot flow. Okay, across the open terminals. So this is it. So I'm assuming, just assuming, that's it, nothing else. Current won't travel actually. Current will not travel. Okay, so this is positive terminal. This is negative terminal. This is positive terminal. This is negative terminal. So let us assume this is also positive and negative. Now let us apply KVL in this open loop terminals. If you apply KVL, okay, so I have not even mentioned their KVL. Why? Because current will not flow. That's why. So now if you apply KVL, what can you write? You just start your journey from terminal A. So there is 2 ohms resistor here. There is 2 ohm resistor. What is the current in this 2 ohms resistor? What is the current? Current I is flowing. Okay, current I current flows through which resistor? This 2 ohms resistor. So you can write 2 into I. Where is my cursor? Yeah. You can write 2 into I. Okay. Plus 6 volts is there. Voltage source is there. So you write 6 volts plus, and the resistor is here. So 2 into, what is the current in this resistor? What is the current in this resistor? I value. What is current in this resistor? It is 0. No current is there. Current will not flow at all. So 2 into 0 plus, okay, You see, you just observe the whatever assumed direction that I have assumed here, current direction. Of course, current is not there, but just in order to write the KVL equation for this open loop terminals, I have mentioned these arrow marks, assuming that it is current, but it is actually in practice. In practice, current will not flow. So you just observe, this was my positive, this was my negative. So our direction of the current that I have assumed here is traveling from positive to negative. After coming here, the direction of current is from negative to positive, so it is not plus, it should be minus. Okay, it is not plus, it should be minus. Minus what? Minus how much? 10 voltage. Minus 10 is equal to 0. Okay. So I hope, I don't know whether you people have, whoever is listening, they have understood or not. So what is KVL equation across AB terminals? Voltage equation across AB terminals. What is it? This 2 ohms into this current I. Okay, 2 into I plus 6 volts. 6, 2 into I plus 6 plus 2 into 0. 2 into 0 plus, not plus, minus. Why minus? Why minus? Why? Because current can enter only through positive terminal and should leave negative terminal. But here what is happening? It is entering at negative and leaving positive. That's why minus 10. Okay, this is minus 10. So there it seems it has that minus has been attached here. This is minus 10. Okay, minus 10 is equal to what? 0. Okay, I have written KVL equation for this open loop terminal A and B. Okay, so I hope you have understood. So now, so to find VThevenin, we have written the voltage equation 6 plus 2I minus VTH. Oh, of course, I forgot about the terminal VTH term that we have already assumed. That also we have to consider. So once again, I will just mention that loop. Okay, so I will mention the loop. So how was it? This cursor is very sensitive. So if you observe the direction which I have assumed earlier, same direction I have assumed now also, same direction. Even now I have assumed the same direction. So the current that I have assumed here, it is traveling from terminal B to A. B is negative, A is positive. That's why minus VTH you also add minus VTH here. Okay. So why minus VTH? Why? Because the assumed direction which I have assumed here earlier, the current direction, even though the open terminals are there, I have assumed some current direction. That current direction is, according to that current direction, the current is traveling from negative terminal to positive terminal. That is why. So this is it. This is our VTH. I'm sorry. This is our KVL equation for this across the open loop terminals. So usually we should not write the KVL equation across open loop terminals, but we have assumed here, for just for namesake, we have assumed VTH is our source. It is acting like a source. Okay, even though it is not the source, just we have assumed, just for the namesake, we have assumed it as the source. So just simplify the above equation, you will get VTH is equal to 6 plus 2I minus 10. What is I value? Just now we have calculated. I value is minus 0.75. Substitute that, you will get VTH is equal to minus 5.5 volts. Okay, so Thevenin voltage is what? Minus 5.5 volts. So whenever you get voltage or current negative, that means that whatever direction that you have assumed for current was opposite to the actual direction, and for voltage, or whichever terminal you have considered positive, that is negative, and whichever terminal that you have considered negative, that is positive terminal. So what are all the terminal notations that you have assumed here? Here you have assumed terminal A as positive, terminal B as negative. For that, what is the Thevenin voltage that you have got? Minus 5.5. Okay, so V Thevenin will become plus 5.5 if B is positive and A is negative. Okay, just opposite. If B is positive and A is negative, VTH is equal to 5.5 volts. Okay, now let us calculate let's go to step 2 and calculate the R Thevenin. To calculate the R Thevenin, so if you observe in the above given circuit, in this circuit you just carefully observe, only voltage sources are there. Okay, only voltage sources. This is one voltage source, this is one voltage source, this is one voltage source. Only voltage sources are there. No current source is there. And what did I say? To determine RTH, all the voltage sources must be short circuited. So if you short circuit all the voltage sources, this is the circuit that you will get. Okay, this is the circuit that you will get. So if you observe here in this circuit, okay, if you observe carefully in this circuit, this 2 ohms and this 2 ohms both are connected. How are they connected? They are connected in parallel. They are connected in parallel. Okay, I am unable to write parallel here. It's okay. Okay, this 2 ohms and this 2 ohms both are connected in parallel. So if you simplify this 2 ohms and 2 ohms, what do you get? 2 into 2 by 2 plus 2. Okay, and this parallel combination is in series with this 2 ohms. So what is RTH? 2 parallel with 2 plus 2. RTH is 2 parallel with 2 plus 2. So which are the parallel elements? These two are the parallel elements. So if you simplify this, 2 into 2 by 2 plus 2, what do you get? 2 into 2 by 2 plus 2, 4 by 4, you will get 1. So what will happen to your circuit? You can redraw the circuit. So if this is your terminal A and if this is your terminal B, okay, then okay, it has gone. Okay, it's okay. So this is one resistor and this is another resistor. So this is our 2 ohms. And after simplifying this 2 ohms and 2 ohms, what you will get? 1 ohm. Okay, you will get 1 ohm. So 1 ohm and this 2 ohms, they are connected in series. This 1 ohm and this 2 ohm, they are both are connected in series. Okay, therefore add them, you will get 3 ohms. You will get 3 ohms. So RTH is how much? 3 ohms. Simply, if you know how to simplify the circuit, R equivalent, how to determine the R equivalent for the given circuit, if you know that usually that is a basic subject. Usually in first BTech first semester itself, you people will learn how to determine R equivalent. So that's the same thing. Okay, that's what we have done here. Okay, so RTH, what you will get? 3 ohms here. So now we have determined VTH, we have determined RTH. Now what we can do? We can draw the Thevenin's equivalent circuit. Okay, and we can connect the load across the Thevenin's equivalent circuit. So let us go to step number 3. So in step number 3, to find the value of RL. Okay, so what is Thevenin's equivalent circuit? See here. So Thevenin's equivalent circuit. So see here, I have got negative, isn't it? I got a negative minus 5.5 volts. Okay, that's why, that's what I have mentioned. If you remember here, what did I mention? Terminal B is positive with respect to A, because when terminal A was positive with respect to B, Thevenin I have got minus. Okay, if B is positive with respect to A, then VTH is equal to 5.5 volts. Okay, VTH. That's why you see here in this circuit, this is my B terminal. So positive I have written towards B, negative I have written towards A. Okay, so that's why the positive and negative terminals are reversed here. Okay, so this is VThevenin, and draw RThevenin in series. So VThevenin is 5.5, RThevenin is 3 ohms. Connect RL across RThevenin. So according to maximum power transfer theorem, maximum power will be delivered to the load when RTH is equal to RL. So what is RTH? 3 ohms. So what is RL now? RL is also 3 ohms. Whatever RTH that you get, that is our RL. That's it. Nothing else. For maximum power transfer theorem, whatever RTH that you determine, if you know how to determine RTH, then no need to determine RL. Simply write RL equal to RTH. Okay. So RL is equal to RTH, and whatever RTH that you have got, same thing you write for RL. See, directly I have written here RL equal to 3 ohms. So is it given RL is equal to 3 ohms? It is not given in the question, but I have written RL equal to 3 ohms simply by copying from RTH. I have copied the value of RTH here. That's it, nothing else. So if you know how to determine the equivalent resistance for the given circuit, okay, by removing the sources, then that is nothing but the RTH across the load terminals. Okay, now we have determined the load resistance value. Now let us calculate the maximum power. That's what is asked in the question. So calculation. Step number 4, calculation of P max. What was the formula? VTH square by 4 RTH. We have already seen that while discussing this theory. So we have seen that P max formula is VTH square by 4 RTH. What is VTH? It is 5.5 volts. And what is RTH? It is 3. So 5.5 square by 4 into RTH. That is 3. So 5.5 square by 4 into 3. You just simplify it, you will get 2.52. Okay, you will get 2.52. So if anyone have any doubts regarding this maximum power transfer theorem, I have solved one numerical problem. That's it. I am going to discuss reciprocity theorem now. So if you have any doubts, you just mention in the chat box. I will just clarify it. I will try to clarify that. I will try to clarify your doubt. So that's it. So maximum power transfer theorem, it's just the extension of Thevenin's theorem. So if you know how to determine VThevenin, if you know how to determine RThevenin, that's more than sufficient. For half of your maximum power transfer theorem numerical problem will be solved. After that, simply you write whatever RThevenin that you have got, you just replace it with RL. So RL is equal to RTH. You just write it down. RL value as RTH. And after that, if you know the formula for P max, okay, if you know the formula for P max, this is the formula for P max. You just substitute VTH and RTH. You will get the maximum power delivered to the load by the source for the given circuit. Okay, so now let us discuss reciprocity theorem. So reciprocity theorem, the statement is, in any linear bilateral network, if there is a single source, okay, if there is a single source whose value, let us assume, is V volts, okay, if there is a single source in a given linear bilateral network, okay, if in a given linear bilateral network, if there is a single source, okay, only one voltage source, you can see here, that's what I have written, one voltage source whose value is V. Let us assume the branch in which this voltage source is connected, it is branch A dash, and it produces a current. This source produces what? It produces a current of I amperes in some other branch. Okay, let us assume that branch is B dash. Okay, so voltage source in branch is in branch A dash, and it is producing a current. Okay, this voltage source is producing a current in some other branch B dash. Okay, that's what is happening till now. Now if suppose this voltage source is removed from branch A dash, it is removed from branch A dash and it is inserted in branch B dash. Okay, Now voltage source which was in branch A dash, it has been removed and it has been inserted in branch B dash. Then it will produce the same current. Okay. Okay, it will produce the current. It may be same, mostly it will be same. Okay, it will produce the current in which branch? In A dash. Okay, it will produce some current in A dash in such a way that if you take the ratio of V by I or I by V, okay, V by I or I by V for both branches, okay, I am considering V by I. Okay, so this is for when source was in branch A dash. This is the V for when source was in branch A dash. This is the V when source has been removed from A dash and connected in branch B dash. Then these two ratios, the response, ratio of voltage by current, okay, that is known as response. Response in both the branches will be same. According to what? According to reciprocity theorem. Okay. So if you have not understood, then I will explain it with the circuit diagram. So let us consider a network. This is a network. Okay, let us consider a network. This is our branch A dash. In between branch A dash, what is there? There is a voltage source. Okay, there is a voltage source between A dash, and there is another branch B dash. There is another branch B dash, and because of this source, current of I amperes flows through B dash. Current of I amperes. This is our I current. It is flowing through branch B dash. Okay, because of V in A dash, I flows in B dash. That's it. Okay, now if suppose V source voltage is removed from A dash and it is connected across B dash. Same source, okay, it has been removed and it has been connected here in branch B dash. Then in branch A dash, current will flow. Okay, it may be same current, may not be same current, but mostly it will be same current. But if you take the ratio of V by I for this circuit, if you take the ratio of V by I or I by V, okay, it can be V by I or I by V, both will be equal. Okay, so that is known as, the ratio of V by I is known as response. Okay, the response will be same for both these circuits. Okay, the response, that is V by I ratio or I by V ratio, will be same for both these circuits. So if you have confused, then it doesn't matter. While solving the numerical problems, you will get the clarity how reciprocity theorem works. Okay, so we will solve some numerical problems, 1 or 2, and we will conclude this class. Okay, so once again I will just discuss this statement which I have already discussed. If in a given linear bilateral network, if there is a single source, okay, of V volts in branch A dash and it produces a current I in branch B dash, then if source voltage V is removed from A dash and inserted in B dash, then it will produce a current I in branch A dash. So the ratio of response to excitation, okay, response to excitation. So here what they have considered here is, response means, the actual definition of response means output. Response means output. Excitation means input. So here V is our excitation. Okay, V is our excitation. Okay, V is our excitation. Current is our response. Always remember, response means output. Current is our response. So the ratio of excitation to response or response to excitation, we can consider either way. The ratio of excitation to response for this network will be same as ratio of, what is our excitation? This is our excitation. Okay, what is our response? This is our response. Okay. So response to excitation of both the circuits will be same. Okay, that is V by I value or I by V value will be same for both the circuits. So let us verify reciprocity theorem for the given circuit. Okay. So let us solve some numerical problems to verify this reciprocity theorem. So here to verify reciprocity theorem for the given network, this is the figure. You can see a DC voltage source of 20 volts across terminal A and B. Okay, there is a voltage source between terminal A and B. Okay, so it's better if I write, instead of writing here A, I can write A here and B here. Why? Because this source and this resistor both are connected in series, isn't it? This source and this resistor both are connected in series. 2 ohms resistor and this 20 volts voltage source both are series. Instead of writing A, B here, I can write here. But in the question itself, they have mentioned terminals A and B. So I can't modify it, isn't it? I can't modify. So who am I to modify? Whatever question that is given, we must accept it as it is. Okay, so I can write it here. You can write it there, but we must write the question as it is. That's why. So now here there is a 2 ohms resistor. This is our 3 ohms resistor. This is 2 ohms resistor. And across terminals C and D, there is a 2 ohms resistor. And they have mentioned current I here. Okay, they have mentioned current I. So what is this? This is the excitation. 20 volts is what? Excitation. Source value. Source value is our excitation. Excitation. So this I, current I, is our response. Response means output. For the given input, you will get the output for any system, isn't it? Okay. So this is our excitation. This is our response. Okay. So 20 volts is the excitation and we don't know I value, isn't it? We have first of all calculate the I value. So what is our aim now? First of all, we have to calculate the I value and later we have to take the ratio of voltage by current or current by voltage, our wish. So this is it. Now let us solve this circuit to verify reciprocity theorem. So first of all, let us calculate the equivalent resistance. Okay. So for that, I am determining the equivalent resistance from the source terminals. So I have removed the source here. Okay. So don't compare it with your Thevenin's theorem. There is no load here. Okay. So of course, wherever current we want to measure, that you can consider it as load, but don't compare this theorem with your Thevenin's theorem. So in this circuit, so wherever source was connected from those terminals A and B, I want to determine the total resistance, that is equivalent resistance. So this is my equivalent resistance circuit. Okay, so this is my equivalent resistance circuit. So if you carefully observe here, if you carefully observe in this circuit, this 2 ohms and this 2 ohms, they are connected in series. Okay, this 2 ohms and this 2 ohms are connected in series. If two resistors are connected in series, what you can do, you can simply add those resistance values, isn't it? So these 2 ohms, always remember, whenever you want to determine the equivalent resistance or total resistance, wherever you have written R equivalent, you must start simplifying the circuit just You just go to the just opposite side of R equivalent. This is my R equivalent, isn't it? I must go extreme opposite to R equivalent. From there, I must start simplifying step by step and until I reach R equivalent, okay, location. So here I have written R equivalent across AB, okay, A and B terminals. I must start simplifying the circuit from CD terminals, okay. Now this 2 ohms and 2 ohms, they are connected in series. So what do you get? 2 plus 2, you will get 4 ohms, okay. You will get 4 ohms. 2 plus 2 is 4 ohms. So what is our modified circuit now? Modified circuit is what? Whatever elements, this 2 ohms and this 3 ohms, they must remain as it is. So 2 ohms and 3 ohms, they are as it is. And 2 plus 2, what did we get? 4 ohms. So this is our modified circuit. Okay. Now again if you observe, this 3 ohms and 4 ohms, they are connected in parallel. Okay, it's a closed path. There is a node here. That means these two are in parallel. Or you just assume the current direction from here. If current enters, it will travel like this and it will divide like this. That means the 3 and 4 are parallel to each other. So since 3 and 4 resistors are parallel to each other, so you just simplify this or eliminate this parallel path or determine the equivalent of this parallel combination. What is the equivalent of this parallel combination? That is 3 into 4 divided by 3 plus 4. Okay, 3 into 4 is 12 and 3 plus 4 is 7. 12 by 7 you will get 1.7 ohms. Okay, so these two resistors can be replaced by a single resistor whose resistance value is how much? 1.7 ohms. Okay, so we are removing this combination. Okay, if you remove this combination, you can replace it with a single resistor whose resistance value is 1.7 ohms. So my modified circuit is this. So 1.7 ohms and the resistance which we did not consider till now, that is 2 ohms. Now how is this 2 ohms and 1.7 ohms? Both are connected in series. Okay, same current is flowing through both the elements. Same current will flow through both the elements. Same current is not flowing here. Okay, but both the resistors are connected in series. So in series elements, it is understood that same current will flow. So if resistors are connected in series, you can simply add the resistance value. So 2 plus 1.7. Okay, 2 plus 1.7. What do you get? 3.7. Okay, so only one resistor is there. So what is R equivalent value now? It is 3.7 ohms. R equivalent value is 3.7 ohms. So now what did we determine? We have determined the total resistance in the given circuit. What did we determine? We have determined the total resistance in the given circuit. So since we have determined total resistance in the given circuit, how many sources are there in this given circuit? Only one source. So what is the total voltage in the voltage in this given circuit? That is V, that is 20 volts. Okay, source voltage. Only one voltage source is there. So 20. We have determined the total resistance. So we can determine total current. What is total current? Total current is always the current that comes out of the source. Okay, so what is total current? It is the current that is coming out of the source. So this is my source. Whatever current that comes out of this source, that is my total current. Whatever current comes out of this source is known as the total current. So it is the total current. So if you see here, I have mentioned that IT. Okay, this is my total currents. So I know total voltage, I know total resistance. So what will be total current? Total voltage by total resistance. Okay, total voltage by total resistance will give me the total current. So total voltage is how much? Source voltage. What is source voltage? 20. Okay, source voltage is 20. Okay, source voltage is 20. Total resistance, just now we have calculated. What is total resistance? 3.7 ohms. Total voltage 20. So 20 by 3.7 you will get total current as 5.4 amperes. So what is the total current? It is 5.4 amperes. Okay. Now, actually our aim is not to determine the total current, but our aim is to determine the current flowing through these 2 ohms, because in the question itself they have asked us to determine, or they didn't even ask us to determine, but they have asked us to verify this, verify the reciprocity theorem. Okay, since they have asked us to verify the reciprocity theorem, okay, therefore uh, across terminal CD we have to determine the current to verify the reciprocity theorem. Okay, but in the question they have mentioned, I think they have mentioned, isn't it? They have mentioned it. This is our question. So in the question you just observe, they have mentioned this current. I'm unable to take the pen. This is my pen. They have mentioned this current. Okay, so current flowing through 2 ohms, and they have given the source voltage. So we have to determine the I value. That's it. So let us determine I value. Okay, I total, how much did we get? 5.4 amperes. Now we have to determine I value. Okay, so I total is the current that is entering this node, some notation K I have given. Okay, and that current will divide into 2 parts. Okay, so total current is entering, current is dividing into 2 parts. That means to determine I value, I can go for the current division rule. To determine I value, I can go for current division rule. So what is, according to current division rule, what do I have to determine? I have to determine the current in branch CD. So what is I? I is equal to total current. Okay, I will just copy that image here. Okay, so see here, I have copied the image here. So if you see here, what is I is equal to? I is equal to total current into what I is in this branch. Okay, I is in this branch. You see, whatever current flows through this 2 ohms, same current will flow through this 2 ohms also. Okay, so in this whole branch, same current will flow. So what is the opposite resistance to this branch? 3 ohms is the opposite resistance. How can you say 3 is the opposite resistance? Why? Because the divided current at this node flows, one portion flows through this resistor, another portion flows through this resistor. Therefore, 3 divided by 3 plus 2 plus 2. Okay, you have to consider the whole resistance in that particular branch. You can't consider only the resistance across which they have mentioned I value. Okay, current direction that they have, it has been mentioned in the question. You can't consider only that. So 3 divided by 3 plus 2 plus 2. Okay, so 3 is what? 3 is the opposite resistance divided by opposite resistance plus or parallel resistance plus self resistance. Self resistance is the total resistance in this branch. Total resistance is how much? 2 plus 2, 4. Okay, so total current how much? Just now we have calculated, that is 5.4. So I is equal to 5.4 into 3 divided by 3 plus 4. So just solve it, you will get I equal to 2.3 amperes. So I value, how much did you get? I value is 2.3. So what is our input source voltage value? Input source voltage value across terminals AB. Across terminal AB, what is the voltage? 20 volts. So what is the current in terminal CD? In terminal CD, what is the current I value? That what did you get? 2.3 amperes. So what is the ratio of input to response? That is source voltage by current, V by I. So what is the ratio? V by I is equal to what? 20 divided by 2.3. So that is equal to 8.7 ohms. Okay, 20 divided by 2.3, that is equal to 8.7 ohms. That's it. Now Now what we have to do, if you have heard me earlier, what is meant by reciprocity theorem? If you have heard me earlier, then you might be knowing that now we have to replace the position of the source from AB branch to CD branch. Okay, now voltage source is in which branch? In AB branch. Now it has to be removed from there and it has to be connected in branch CD. Now this is it. So from branch AB I have removed the source voltage, I have connected in branch CD, and in branch AB what is left over? One 2 ohms resistor was there. The 2 ohms resistor I have drawn it here. Instead it was earlier, it was here. If you have observed carefully, that resistance was here. So instead of drawing it here, I have drawn it here. As I have already told you, in between two nodes, if any resistor is there, if any element is there, you can change the location within the same branch. Anywhere within the same branch, you can change the location of the any element, resistor or capacitor or inductor or source voltage also. Okay. So in the same branch, even if you change the location, it doesn't matter. Okay. So now we have removed the source from AB terminals and we have connected across what? This is my source. I have connected across terminals. What are my terminals? C and D. I have connected across terminals C and D. Okay. Now whichever location earlier source was there, in that location we must calculate what? Current. You must calculate the current here. So you must calculate the current in branch AB. You must calculate the current in branch AB and source voltage, of course no need to calculate. Why? Because this is the current across terminals A and B. You have to determine the current and source voltage, of course. Now it has been shifted to terminal CD. Okay. Now let us proceed and let us simplify. Okay. So first of all, what I want to do is, I want to determine the total current. To determine the total current, first of all, I will determine the total resistance. So let us determine the total resistance. So first step, solution. So I didn't write solution here, I will write it. Already no need to write because we are in the middle of the solution, isn't it? No need to write. So calculation of total resistance. Okay, first of all let us calculate the total resistance. Now wherever source was there across those two terminals, I have written R equivalent, means total resistance. I have written it here. So I have removed the source to determine the R equivalent. Okay. Now if you observe this circuit carefully, 2 ohms and this 2 ohms and this 3 ohms, they are connected in parallel. Okay, this 2 ohms and 3 ohms are connected in parallel. So you just simplify this and determine the equivalent of these two parallel combination. What is it? 3 into 2 by 3 plus 2. Okay, 3 into 2 by 3 plus 2 is equal to what? 6 by 5. You just simplify it, you will get 1.2 ohms. Okay, now you have determined the equivalent resistance of this parallel combination. That is, how much is it? 1.2 ohms. Now so now this is our modified circuit, 1.2 ohms. In series to earlier, what were the elements left over? This 2 ohms and this 2 ohms were left over. You draw them as it is. This is 2 ohms and this is 2 ohms. Okay. Now just compare these three elements. These three elements, those three elements are connected in series. Okay. So I think I forgot to write one term here. This 2 ohms, add 2 ohms and so add 2 ohms and 1.7 ohms, because 1.7, is it 1.2? Sorry, 1.2. Yeah, it is 1.2 ohms. So add all these three, you will get the equivalent resistance, okay, total resistance in the given circuit. So what is the total resistance in the given circuit? 2 plus 2 plus 1.2, that is 2 plus 2 plus 1.2. So what is it? If you add them, you will get 5.2 ohms. Okay, it is R equivalent value is 5.2 ohms. That's it. We have determined the total resistance. Now we can determine the total current. So total current, what did I say? Total current is the current that is coming out of the source from this positive terminal. Whatever comes out of this source, that is our total current. That is I total. Okay, that is total current. So what is the formula? Total current is equal to total voltage by total resistance. Total resistance just now we have calculated. What is total voltage? That is the source voltage. So 20 by 5.2. So I total is equal to 20 by 5.2. You just simplify it, you will get I total is equal to 3.8 amperes. I total is equal to 3.8 amperes. Okay, so total current is 3.8 amperes. So we have determined total current. Now if you observe, this total current comes out of the source, it flows like this, it will flow like this, it will flow like this. At this junction it will divide. So what is the current that we have to determine? The current flowing through this 2 ohms. So current flowing through this 2 ohms we have to determine. This 2 ohms resistor we have to determine. Okay, so current is dividing here. That means 2 ohms and 3 ohms are connected in parallel. So you can go for current division rule. You can go for what? Current division rule. So we have to determine current in which branch? AB branch. So by current division rule, what is it? I is equal to, okay, I is equal to I total into opposite resistance to 2 ohms was 3. So I will just copy that image here. Okay, so you can see here this is the total current, this is the current that I have to determine, and current is dividing here. Okay, so I is equal by current division rule, I is equal to what? Total current into, I want to determine current flowing through 2 ohms. So what is opposite resistance to 2 ohms? 3. So 3 divided by 3 plus 2. Okay, I total into 3 divided by 3 plus 2. So what is I total? 3.8 into 3 divided by 3 plus 2 is 5. So 3.8 into 3 by 5. You simplify it, you will get I value is equal to, I value, what is it? 2.3 amperes. What is I value? It is 2.3 amperes. I am erasing all links. I am going to delete this image also. So that is it. Now we have determined I value. What is input source voltage current in branch? This is current voltage in, now this voltage source is in CD branch and current is in AB branch. Okay, so current is in AB and source voltage. We have removed the source from AB and we have connected it to CD. So now input source voltage is in which branch? CD branch now. Okay, so it is in CD branch, and current is in, current that we have calculated just now is in AB branch. So this is it. I have written here AB. So that current is 2.3. So what is the input to the response ratio? Input to the response ratio. What is V by I? V is 20. I is 2.3. How much did you get? 8.7 ohms. Why I have written ohms? Why? Because it is the ratio of V by I. That's why I have written ohms. So what is it? 8.7 ohms. So source voltage is in which branch now? Source voltage is in CD branch. So what about the previous case? Let us go to the first case. How much did we get? How much did you get? Here this is the first case when the source was in AB branch. Okay, and the current in CD branch, how much did you get? 2.3. So what it is the ratio? What is the ratio that we have got earlier? It was 8.7. Okay, when source was in AB branch and current is CD branch, the input to the response ratio, you have got 8.7 ohms. Similarly, when voltage source is in CD branch and current is in AB branch, what is the response that you have got? That is, input to the response ratio. What is the ratio, V by I ratio that you have got? 8.7. Both are same, isn't it? Both are same. Okay. So in both the cases, the ratio of V by I value, okay, the ratio of V by I value is same. Hence, reciprocity theorem is verified. Okay, since V by I value that is 8.7 ohms, 8.7. In both the cases, we have got 8.7 ohms. Hence, reciprocity theorem is verified. Okay, let us see one more small numerical problems. One more problem, and I will conclude within 5 minutes. Okay, so verify reciprocity theorem for the shown figure. Okay, for the circuit shown in the figure. So this is the given circuit. So if you observe here, there is a current source of 10 amperes across AB terminals, and there is a resistor of 1 ohm and resistor of 2 ohms and 3 ohms resistor across CD terminals, and they have asked us to determine, they have mentioned V here. Okay, and what we have to do? We have to verify reciprocity theorem for this given circuit. So current source is given across AB and V is mentioned across CD. Okay, V is mentioned across CD. So we have to determine voltage across 3 ohms resistor. Okay, we have to determine the voltage across 3 ohms resistor. So first of all, to determine the voltage, I must know the current. V is equal to I into R. I know R value. What is R value? R value is 3 ohms. If I am able to determine the I value also, current flowing through this 3 ohms resistor, then I can simply multiply I into R. I will get V value, isn't it? It's very simple. So here already we have a current source of 10 amperes. That current will flow like this at this node. What is happening? This cursor, I don't know why. Okay. I wanted the eraser and so this is it. This is our node, isn't it? So at this node, what is happening? Current will divide. Current will divide. Okay. So I can go for current division rule. Okay, to determine the current in this 3 ohms resistor. So I will just remove all inks. So what is the current in 3 ohms resistor? Current in 3 ohms resistor, see I have written I 3 ohms is equal to total current. What is it? Total current is 10. 10 into, so this 3 ohms and this 2 ohms are connected in parallel. So what is parallel resistance of 3 ohms is 2. So this is 2. 2 divided by 2 plus 3. I have written 3 plus 2. It doesn't matter. Okay. So 10 into total current into opposite resistance by opposite resistance plus self resistance. But I have written self plus opposite. It's okay. 2 divided by 2 plus 3. Okay. So 10 into 2 divided by 2 plus 3. You just solve it. You will get some 4 amperes. So what is it? 4 amperes. Now what is V value? V is equal to I into 3. So what is I value? 4. Okay. So V is equal to 4 into 3. How much do you get? 12. Okay. So how much V value is? 12. So this V value that just now we have calculated how much? It is 12 volts. V is 12 volts. What is I value? Across branch AB, it is 10 amperes. So now what is the ratio of current to voltage? You can, and I have already told you, you can write current by voltage or voltage by current. Here our source is current, that's why I am taking current by voltage ratio. So current is 10 and voltage is 12. So 10 by 12 you will get 0.833 mho. Okay, since it is mho, why mho? Okay, mho means mho symbol. I will just draw it. Where is my cursor? Here. Cursor, yeah. Mho. This is the symbol of mho. Okay. So mho symbol. So it is admittance, not impedance. Okay, that's why mho symbol. So this is it. Ratio of current by voltage. How much did I get? 0.833 mho. Okay. Now remove this current source from here, and place it somewhere here. Let us go to the next circuit. This is it. See, I have removed current source from terminal AB and I have connected current source. So current source should be connected in parallel. Voltage source should be connected in series. So current source should be connected in parallel. So here, not here. Okay, it should not be connected in series. It should be connected in parallel. So here across 3 ohms resistor, I have connected current source in parallel, and here AB terminals are open now. Okay, AB terminals are open now since we have removed the current source. So what is across AB terminals? It is V. V is across AB terminals. Now current source is across CD terminals. Now this current will come at this junction. Okay. This is the current coming at this node C. What is the current at node C? It is 10 amperes. That current will flow like this. Of course, here current cannot divide, isn't it? Current cannot divide at all. At this node, this is not at all a node. Why? Because AB terminals are open. Means current in 1 ohm, current flowing through 1 ohm is 0. How much current flows through 1 ohms? Through 1 ohms, current flowing through 1 ohms is 0. So you should not consider this resistor. Why? Because current is not flowing through this resistor. So simply from the source current flows through this. At this node current is this. Entering current is 10 amperes, and it will divide between this 3 ohms and 2 ohms. But in 1 ohm, no current will flow. Okay. So what is the current flowing through 2 ohms? This current flowing through 2 ohms. You can't determine current flowing through 1 ohm. Why? Because it is connected to an open terminal. So let us determine current flowing through 2 ohms, because this voltage is across, this V is across this 2 ohms now. Once again I will erase and I will draw. So since no current flows through this 1 ohm, because terminal AB are open, so V is across 2 ohms. V is the voltage across 2 ohms now. So V is the voltage across 2 ohms. So current flowing through 2 ohms is total current, that is 10 into what is opposite to 2, that is 3. So 3 divided by 3 plus 2 is equal to, you just simplify it, 10 into 3 divided by 3 plus 2, you will get 6 amperes. So what is V? V is equal to what? V is the voltage across 2 ohms. What is the current in 2 ohms? 6. So 6 into 2, how much do you get? 12 volts. 6 into 2, you have got 12 volts. Now let us see the current to voltage ratio. What is it? Current is 10, voltage is 12. 10 divided by 12, what did you get? 0.833 mho. Okay. So you will get 0.833 mho. Okay. So if you compare this admittance value that you have got 0.833, when current source position has been changed from, it has been removed from AB and connected across CD, you just compare it with the previous case. What is the ratio here? In this previous case, when current source was here, okay, so what is this admittance you have got? Current by voltage ratio, what did you get? 0.833 mho. When current source is here, admittance value, how much did you get? Current by voltage ratio 0.833 mho. So both are same. Hence reciprocity theorem is verified. Okay. That's it. So this is about maximum power transfer theorem and reciprocity theorem for this session.